topic. And you've seen today's topic is like code coupling and multi-scale, multi-physics modeling. So like this, we'll have different topics for each of the seminars. So the next one, there are some proposal on multi-phase unboiling. We are still collecting suggestions for the speakers. So basically, everyone is welcome to suggest top speakers and also topics. And we made this not particularly like regular in the sense that we want to put this in the right time, so that it won't clash with other activities organized on this, on nuclear topics. Other things happening in this area. So what else do we have? I'm hoping we have 3 speakers today, and I'm hoping, I actually know each one will be quite interesting, especially for myself and for our research. So we hope to get Antoine Gerschenfeld from CEA, and then this is like a guest lecture, and then followed by 2 lectures from the UK. And at the end, we'll have a general discussion on this particular topic. And if there are additional questions for the speakers, then we can ask questions at that time. Now, I really do not have a lot more to say, but all the lectures will be recorded. Hope everyone's happy with that. And then those recorded lectures will be made available through the website. And the website hopefully will be online, available very soon. Can we now check if Antoine here? And we, you haven't heard anything from him yet?
No, not yet.
Yeah, actually,
we can
I just received an email from him. He said, I'm trying to connect to the Zoom link, but I apparently also need a passcode. And Wei, can you reply to see that?
No, but I have sent him the link and passcode just a few minutes ago.
Okay, now I've just, the code is 131162, and I send now. Hopefully, Tony will get it. Okay, while we are waiting, I just briefly introduce Antoine. So he's got his PhD from École Normale Supérieure in France in 2012. And very soon after that, he joined CEA's Thermal Hydraulics and Fluid Mechanics section. And then he's been there ever since. In that organization, he has led the development of a sub-channel thermohydraulic code, Trio MP, and also he's involved in the development of 2-4 coupling codes and fine models in single reactor scale simulation called MATHIS, and has been involved in many international collaboration. And so, as I said, he's an expert on this topic, so hopefully we'll have him here very soon. Antoine, yes, I've seen you are here.
Oh, sorry for the delay.
All over the link and everything. So basically, you probably noticed that I've just introduced you. And so as soon as, if you are ready, so we can hear your screen. And if you could actually talk for around about 30 minutes, and then we have 5 minutes questions and answers after that. That's okay.
Yes, no problem. Thank you very much for the introduction, and sorry for the small technical problems I had. So let's see if it works the first time. Let's see. Oh. One second. Oops. Yes. Like this. Maybe only the window. Up. Let's see.
Yeah, I mean,
is it working?
Okay, great. We've seen it.
Ah, super. Thank you. So, good morning, everyone. And as Shuisheng just said in the introduction, I'm Antoine Gerschenfeld from CEA, and I'll be giving a talk about multiscale and multiphysics simulation with a focus on the CEA experience as applied to advanced reactors, and this will mainly mean sodium fast reactor in our case. So so the main goal of this is traditionally when we for all the fast reactors that have been developed in the past and licensed, the approach that has been retained, especially for the thermal hydraulics, has been to use a system code. So system code mainly means RELAP or Qatar or SAS. And this is how historically transient have been analyzed for these reactors. So for instance, the loss of flow transient, protected or unprotected, the loss of heat sink, and so on. And this has actually given satisfactory results. Licensing has been accepted, and so on. However, when you look into this in a little more detail, and this is especially the case for new reactor designs, you start to see that there are complex things that can affect these reactors. And so the main big effects are 3D effects in sodium fast reactors. So when you have a large pool full of liquid sodium, the actual flow pattern within the hot pool, within the core, and so on can actually be complicated. And in the past, the way this has been dealt with is that we have used coarse modeling because we didn't have a choice. There were no numerical means available. And this has resulted in high margins in the safety files of reactors, for instance. And when you look at new designs, when you try to make them more compact, more optimized, and so on, this becomes more and more constraining. It also becomes constraining because the safety requirements are actually increasing with time. And so something that was a viable way to license a reactor in the past might not be viable for a new reactor now. And so at the same time, on the scientific side, there has been more and more work on what we would call higher fidelity modeling. So things like CFD and RANS, DNS, and so on. And so one idea would be to say, okay, can we use our R&D on higher fidelity models to improve on our safety justification, especially if we have a new reactor? And this is actually what I will talk about with a few applied examples. So this will be in both cases on sodium fast reactors, like this Astrid reactor you can see on the left here. And first I'll talk about the problem of decay heat removal. So this is a purely thermal hydraulic problem, and then a bit about multiphysics modeling. So this will be about the ULOF, the unprotected loss of flow transient, in an SFR with one of these new cores that have a low sodium void warp. So first, let's talk a bit about DHR. So in modern sodium fast reactor design, DHR is usually performed by putting a heat exchanger inside the hot pool of the reactor. So this is a simplified picture of the hot pool. There's the core at the bottom right there. And the heat sink in the whole primary circuit, when you are in the decay heat removal regime, will be a heat exchanger in the hot pool like this, connected to a small circuit in sodium that can go through natural convection. And this circuit will actually be able to remove the heat to a chimney at the top of the reactor building. And so when you design a decay heat removal system like this, what actually happens is that when you look at how the flow looks like in the primary circuit, the flow can do more or less the same thing that it was doing in the nominal regime in forced convection. So this would be going up into the core, being cooled a bit at the output because the heatsink is there, but then going down in the heat exchangers, down into the pumps, and then below the core in the diagrid, and then back up. But if the heatsink is here, there are also some alternative pathways. And one of these paths is just sodium being cooled here, going down straight into the core, maybe down into one of the cooler subassemblies at the periphery of the core, and then doing a U-turn inside the diagrid at the bottom, the inlet core plenum, and then back up. And another thing that can happen in sodium fast reactors is that because the subassemblies in these reactors are closed, unlike PWR subassemblies, for instance, you have small gaps between the subassemblies on the outside. And these gaps are not connected to the inlet plenum at the bottom, but you can still have sodium going down, cold sodium going on the outside of the core like this, going sideways between the subassemblies, heating up around the center of the core and going back up. And if the reactor behaves like this, it's actually quite hard to compute how the heat is actually removed. For instance, if you use the traditional approach with a system code, this whole pool of sodium, like right here, will be described by one mean temperature value. And so you have some chance of describing this normal path right here, but these two paths here, so with sodium going down in some places and up in the center, this is impossible to describe. And then, so this will have a few consequences. The main one is that you will predict a higher core temperature than if you add an actual fine description method, because if you use a coarse method, these paths number 2 and 3 will be badly either neglected or completely miscalculated. And so everything will be removed by this path number 1. So if you have less means to remove it, then you expect to have higher core temperatures. And this could be acceptable from a conservative point of view. But the other thing you will do is that if you assume that the only heat removal mechanism in action is this one, you will make it work over time, and this will lead to a higher flow rate than you would have in reality. And this means that, for instance, all the temperatures in the rest of the reactors will be wrong, and then it becomes very hard to actually understand if the calculation is conservative or not. So this is the kind of justification for having a finer approach to modeling this thing. And it's always easier to see with a real example. And so a first example of this kind of thing is actually the UK sodium fast reactor, PFR. So PFR, so that this was a 250 megawatt electrical at the very, very top of the UK. And this one had actually a decay heat removal mechanism like this. So the decay heat removal was by some coils located in the hot pool on top of the intermediate heat exchangers, actually. So you had the core here. Normally, the sodium would flow in the intermediate heat exchanger here, down, then into the cold pool, then into the pumps, then down into the core, down through this pipe into the inlet plenum of diagrid, and then into the core. And so for PFR, the mechanism 1 that I showed in the previous slide is actually this one. And you can already see that the path is quite long and complicated. And alternatively, the sodium can do this. It can go up from the core, get cooled here, bypass all the things at the bottom, go back on the side of the hot pool like this, get down in one of the external subassemblies, and then go back up. So you can already see on the drawing that this is a much shorter path for the sodium, and it's actually probably going to go there. And then there is this loop that goes between the subassemblies that's even shorter. And so what was actually noticed when natural convection tests were done in this reactor was the primary flow rate was not what was expected. It was lower. And the outlet temperatures in the core were not what were expected either. They were higher in the center and lower on the side. And overall, the reports mention complicated flow patterns going on within the reactor. And this is more or less what we would expect if you think that these green and blue paths can play a role. And so at the time these tests were done in PFR, there was no large-scale application of CFD. There were probably not a lot of detailed measurements in the reactor, and so it was hard to understand what was actually going on. And then if you do a 30-year jump forward in time, when we were designing the Astrid reactor in France, we made detailed CFD simulation of this kind of mechanism, and we could have a little more visual view of what was going on. So this is the Astrid design. So you have the core in the middle, the sodium goes here, heats up, goes into the hot pool here, then goes down in these intermediate heat exchangers into the cold pool and gets picked up by pumps and goes back in the core. And this is what it looks like in normal operation, forced convection, and the pumps go, so 1500 megawatts thermal and forced convection. And when it's in long-term decay heat removal mode, it looks something like this. So you have a very strong chimney effect in the center. Sodium actually goes up in the middle. This part is actually quite hot, and this is where the heat sink is. So this gets cooled down. Some cold sodium gets injected like this and goes around the core like this and cools it back. And for this case, we could also compute what would be the consequences of the different types of model we could use. So this is the produced type, so the Astrid reactor. And in this case, I've plotted the primary flow rate computed by different methods. And in red, you have the flow rate computed by the simplest approach, which is system code, so like RELA, for instance. And you can see, so the flow rate does something at the beginning, and then it establishes a steady state value, and then it goes up. And then when we did our first more detailed calculation with some CFD in the pools, we saw a flow rate that was lower and going down. So we said, oh, yeah. So we had a problem because our first estimate, the simplest one, was not conservative at all. Then we tried to do something to correct a bit this simple estimate. We figured that what was going on is that we had, so in nominal state, we have a heat exchange between the two pools in this left picture. And this is a heat exchange between two pools that are more or less at homogeneous temperatures. And when you're in natural convection, this is completely false. The pools are stratified on each side. And so if you use a simple method for predicting the heat exchange, it will be wrong. So what we said is, okay, maybe if we set this exchange coefficient to 0 in the simple method, we will improve our flow rate calculation. And this actually works more or less. It moves you from the red curve to the green curve right here. So it's it's more conservative than the other one. And then we did our first calculations that took into account everything. So CFD in the pools and subchannel and CFD in the core. And we ended up with this purple curve. And so in this final case, even the best we could do from the simple method, the most conservative estimate, was not conservative anyway. And this is the kind of justification we had to move to coupled complex calculation. And in this case, the overestimation can actually be something like 150% at this time. So this is more or less the motivation for moving from the simple system code calculation to the more complex approach. And then, of course, the question becomes, what can we do? So the first thing that can be done, and that has been attempted in Italy, for instance, is to say, okay, even in our simple system codes, nowadays, they usually have a 3D module, like, for instance, the 3D module of RELA or the 3D module of Qatar. And we can start from our simple system calculation and move to this 3D module without a lot of efforts because it's already been coded for PWRs. The problem in this case is that these 3D modules have a very limited resolution. They can do tens of meshes in each direction, but it's already expensive and the codes are not parallelized, so it becomes very slow. Usually it works when you want to compute stratification, but when you have a jet of fluid coming into a plenum, with this kind of meshes, it's almost impossible to predict it correctly. The next thing you can say is that, okay, nowadays we've got CFD codes, like Fluent or Star CCM, and I can model my entire reactor with inside one of these codes. So if you do that, you will have a high resolution everywhere. So these phenomena like stratification and jets will be predicted more or less correctly. But then, of course, the problem becomes a CFD code is not a nuclear safety code. And so all the work that was done in the system scale nuclear safety code in the past, like having models for the pumps, the heat exchanger, the point kinetics in the core and so on, you will have to do them again, which is, and you will have to do them again and also redo all the validation work, which is even longer to do. The other problem with this scale is that, well, if you do everything within the CFD code, you will have CFD absolutely everywhere, including in parts of the reactor that are not very complex from a CFD point of view. And so this can actually be quite expensive. And then the last thing you can do is you can say, I will try to combine 1 and 2. So this would be trying to couple together to do a single simulation with both some parts in the system scale and some parts in the CFD code. So the advantages of this is that you can reuse all the models that were already in the system scale. When you use fine resolution, you only have to use it where you need it. For instance, if you have the bottom of the reactor that's more or less that has a very flat temperature profile, you can exclude it from the CFD. The big disadvantage is that you have to develop a way to do this single simulation with 2 codes, which is what we would call a coupling algorithm. And then you have to develop it, and then you have to validate it in a way and justify that it will be suitable for a safety calculation. So there are 2 main ways of doing this, of coupling 2 codes together. So the first one is to say, okay, I have a coarse model, the system scale on the left side here. I'm going to remove part of this model. So there will be a big hole inside the system model. And on the other end, I will develop a new CFD model, which will be this one. And I will couple them together by exchanging things at boundary conditions. So for instance, I take the flow rate coming here and put it as a boundary condition in the CFD, and I take the pressure here and put it back as a pressure boundary condition here. And this has the advantage of clarity, because you only have to organize exchanges at these boundaries like right here. And it has a disadvantage, which is that usually there are convergence difficulties. And this usually comes for the resolution of a common pressure field between the codes, because the pressure field in this calculation, usually the fluid is almost incompressible, so pressure fluctuations propagate very fast. And if they have to propagate from one code to the other, this can be really slow. Another thing that you can do is you say, okay, I will keep everything on the system side. So the system model will still include these parts that you actually want to compute with CFD or something fine. And so the advantage of this one is that the stability issues are much lesser in this model. For instance, if you need to propagate the pressure, well, it will still propagate inside this gray zone right here. But the disadvantage is now you have to make sure that what's going on in there is consistent with what the CFD is computing. And this actually leads to a more complicated algorithm. So this one is called the domain decomposition, and the one at the bottom is called the domain overlapping approach. So this is actually what we choose to do at CEA. So we have the system calculation here. We inject the temperature going into the CFD domain as a boundary condition right here. And then what we do is that we look at the temperature coming out of the CFD with an appropriate average, and we impose it at the right mesh on the system side to ensure that the flow coming from here to there will have the right energy. The global energy between this and this will be conserved. The situation is a bit more complex on the pressure side, because on this side, what you have to do is that you take the flow rate coming from the system side, you impose it as a boundary on the CFD side, and then if you're in the incompressible regime, you will already have the right flow coming out. And so the question becomes, what's the information that I can take back from the CFD to the system? And the actual answer to this is that what you want is that the system side has to see the right pressure difference between the inlet and the outlet as the CFD. If this is true, then the system side will see the right pressure difference, therefore it will compute the right flow rate in the loop, and the CFD, and this is what will be given to the CFD. And in order to obtain that, what you have to do is that you have to look at the pressure difference on the CFD side, which is the correct side in a way. And then the system calculation, you have to introduce a source term in it, a little force, that you can adjust until this pressure difference is equal to this one. So this actually needs some iterations between the code, but once you do it, it converges quite well and it leads to a convergent calculation. So this is, and what we actually did in CEA is a bit more complicated because we have the system code, which on our side is called Qatar, which we wanted to compute to a combination of two codes, a sub-channel code in the core and a CFD code for the plenums, for instance. And we had to do some complicated coupling algorithm like this, but the principle is the thing I described earlier. And then the big work is actually validation and justification. So actually on the French side, we had the advantages that in 2017, our regulator came up with a guide on how to validate this kind of coupled calculations between two codes. And the rule is actually very simple. When you have something that is a coupling between two codes, you have to validate it as a single entity, as if it was a single code with its validation database. So for instance, if you have two codes that you couple together and you say each of these is validated, it's not enough. This is not a sufficient requirement to say that the coupling is validated. So the first thing is that you must actually have what you need to have a coupling code. You need to have a code that you can apply to the reactor scale, the validation database, and that remains the same. And then at CEA, we did this by developing a kind of generic coupling tool that we call the MATIS for multiscale advanced thermal hydraulic simulation, and that we could apply to the validation experiment and the reactor application. And then the second requirement is that you need to have a VVUQ, verification, validation, and uncertainty quantification for the complete beast. So for instance, you need separate effect tests that describe analytical phenomena, and this will be actually covered by each of the codes inside of the coupling. But you also need combined effect tests, and this one this is a validation database that will describe phenomena that can only be calculated when you couple the codes together. And so this would be outside of the validation database of each of the individual codes, for instance. And then you will need integral validation. An approach we use is that, and that's very important for the regulator, is you have to start from the point that for each transient, the regulator appreciates if you say that you will always use the simplest tool needed. For instance, if you have a forced convection transient, the system scale works and you can use that. No need for a coupled code. The coupling and the multiscale only comes into play when you have natural convection or some dissymmetric phenomena. And the last point is that there is no notion of a generic validation database. For each transient to compute, you have to say, in this case, I am validated because I have this, and this test, and it's applicable to this transient. But still, so when you look at this, you tend to say that, okay, the situation seems to be the same as validating a system code, for instance. But actually, there is a difference. And the difference is that if you use a multiscale or a cold coupling approach, you will have a higher, you will have what we call a better extrapolability. So for instance, if you have a system code and you want a validation experiment, usually you will need to perform an experiment that will have the same geometry as the reactor scale, but smaller, like an integral effect test, like LOFT or BETSI for a PWR. If what you're validating is a multiscale or coupled approach, you can justifiably say that even if the experiment is in a different geometry than the reactor case, the geometry effects are predicted by the CFD, and so I can still learn something from my experiments in a different geometry when I do the reactor application. And so at CEA, this was very useful for us because this allowed us to use experiments that were designed for other reactors. So for instance, one effect that we wanted to validate was this possibility of heat removal by interrupter flow on the core. And for this, we could use an experiment designed for a Japanese reactor instead of for the French design. So this actually saves time and money when you're doing a new design because you don't always need a new experiment. And then, of course, there's the integral scale. And for this one, so we are actually working on we have used and are working on a few things. So we have the Phoenix end-of-life test, so the French sodium fast reactor, and it's the one there. So for this, we had a natural convection test and a dissymmetric test, which is a partial loss of heat sink. And in the international frameworks, there is also a wide availability of access to other reactors, like the American reactors, EBR2 and FFTF. FFTF is this one right there, where there was a test on an actual unprotected loss of flow transient. And it's the object of an ongoing IAEA benchmark. And there's also a Monju test that was shared with the IAEA. So the overall conclusion from multiscale is that actually, for this particular Astrid application in France, we actually were able to move it all the way to being considered as a default safety methodology for dissymmetric or natural convection transients. And actually, we also had some code-to-code benchmark to confirm this on top of the validation database. So there were models like this. This was the Framatome model. This was the CEA model. And the results they gave were more or less comparable. We had a validation database thanks to this extrapolability affair. And the calculation was actually fast enough to be useful for reactor calculations. So it took around 2 days to simulate a few tens of hours of transient time. But of course, there's always something more complicated. So now I need to check the time. And the more complicated thing is multiphysics. So on this, I'll be very fast. So a big feature of new sodium fast reactor design compared to the traditional ones is that in a standard SFR design, if boiling occurs within the core, there will be a positive void coefficient, and it will lead to a very fast power excursion. So the transient that leads to this is usually the unprotected loss of flow. So you stop the pumps and assume the control rods are inoperable. And this, in a traditional SFR design, will lead to a severe accident in a few tens of seconds. And in more recent SFR designs, like the design of the Astrid core or of the BN1200 core or the European ESFR Smart project, we have done something to mitigate this. We have put what we call a sodium plenum above the core, a zone where you have only sodium above the top of the core. And the idea for this is that if the sodium boils, it will start producing void inside the core. It will also void this top zone, and it will lead to increased leakage and a power decrease. So what normally would happen in one of these cores is if you have an onset of boiling, it will lead to a negative reactivity insertion and either an oscillating or a stable regime. So this should be much better than a severe accident, but you need to compute it, of course. And this is actually quite complicated because when you look in more detail at what goes on, the effect of voiding in a sodium fast reactor, it leads to 3D neutronic effects. So if you have voiding like this in the core, so here the blue is an area where the sodium has voided because of voiding, it will lead to this kind of deformation in the power distribution in the reactor. If you want to compute this correctly, there is actually no way to do it with the standard point kinetic models. You need 3D neutronics, like either transport or Monte Carlo, to compute what's going to happen. And so we've tried to do this at CEA. So we coupled, on the system side, we have the Qatar code for the thermohydraulics. And on the neutronic side, we used the Apollo 3, a neutron transport code. And for this, the actual effect, so we were able to perform this kind of calculation, and the actual effect was for this, for the transient we were looking at, if you looked at the standard calculation with the point kinetics, you would predict that the void would get to dry out inside the reactor and something would melt. And if you do the couple calculation, then you actually predict that the dry out is avoided. You instead end up with this kind of oscillating behavior, and the cladding temperature never goes above the saturation temperature, so there's no dry out. But of course, this is actually, when you look in more detail into what goes on, it's a lot more complicated, because on top of this interaction between neutronic and thermal hydraulics, there's also a lot of coupled effects with what goes on inside the fuel. So there's a coupling to pin thermal mechanics, and there is also a potential coupling to motion of the sub-assemblies provoked by vapor bubbles coming out of the core. So this is actually very complicated, and we're just at the beginning of trying to approach this kind of effects. So unfortunately, I have to skip this slide, I think. And so the conclusion from this is that, well, this drive for more compact design and more complex safety calculation in SFRs actually leads to a need for finer scale, finer calculation for the safety justification of the reactor. And so you need to, this led us to move from the normal system scale approach to either multi-scale calculation with some CFD, or even a multiphysics calculation with a 3D neutronics code, for instance. And this has, of course, high requirements on the safety side. So you need to have validation, and you need to be able to say that what you're doing is generically applicable, will perform the same between validation and the application. And for multiscales, I think this can actually be done today. You can develop a new approach, validate it on existing data, and go all the way to a safety application for a new design if you have one. For multiphysics, I would say that one decade or two will be needed to reach this kind of maturity. But in the long term, this should be feasible, and it's actually really important to demonstrate that some new safety features in SFR, like these low void cores, will actually work. So that will be all from me, and thank you for your attention.
Right, excellent. Antoine, that was great to hear the story from CEA. I can see that you've done a great amount of work in this area. So can we have a couple of questions from the audience, if there are any? You can just start to, unmute yourself and speak, unless we have a problem at some stage. Okay, so probably I could start with a simple question. Now you're in the coupling and the overlap coupling, you actually try to make use of the results from the CFD, and you said the pressure is corrected in the system code side, but how about the thermal? And can you actually match both thermal and moment, velocity together with the pressure? Okay,
so for the thermal, this would be this slide here. And actually, what you need to do, so in a little more detail than what I put here, you can look at the amount of energy or enthalpy that is coming out of the CFD, and then you need to adjust this temperature until you have the same amount of energy coming across this little face right here. And so it actually is also an iterative process, but with this, you can guarantee that the energy coming out of here is exactly the same as what's coming in here. So it can actually be done in a conservative way at each time step.
Okay, thank you.
Shuisheng, it's Steve Graham here. I've got a follow-up on that. It seems interesting that the temperature should be varied, whereas analogously, I mean, for the pressure field, we seem to be altering the resistance or changing the momentum, which seems to me to be a truly excellent approach, and I would potentially use if I was doing it. I'm just wondering whether or not for the thermal side, the equivalent is probably to change a heat transfer coefficient on the system side in some way. I'm just interested that the temperature itself should be chosen and the logic behind that, unless I've just misinterpreted the situation.
So in this case, the reason for just changing the temperature right here is more or less that actually, so when you look at this, actually, we don't really care what's going on in this gray part. The only thing that's important is whenever something is going out or coming in, it has to be consistent with the CFD side. And so in our case, just changing the temperature was the easiest way we could do this.
Okay.
And actually, so other groups like in Sweden, I think, have done a method a bit like this, but with the adjustment of heat transfer coefficient or heat source term, for instance.
Yeah.
So
Okay. No, thank you. Thank you.
Okay, I suppose we should stop here. Antoine, thank you again for an interesting talk. We still have time towards the end of the seminar if there are more questions. Okay, and if you could stop sharing, it'd be great. And Wendy, if you